TriStar, I'd like to welcome you all to this TriStar sponsored webinar, Large Assembly Techniques, Designing and Managing Large Assemblies in PTC Creo. Our presenter today will be Product Manager Moshe Baum. Before I hand it over to Moshe, I'd like to go over a few logistical things. First, the webinar will be recorded and posted in our Resource Center, which you can find by going to tristar.com and clicking Resource Center link at the top of the page. Next, if you have any questions during the webinar, please submit them in the Questions tab in your GoToWebinar interface. After the presentation, I will ask the submitted questions to Moshe. With that, I'll turn things over to Moshe.
Thank you. Hi everyone, my name is Moshe Baum. I'm the Product Manager in PTC Creo CAD segment, responsible for assemblies, including top-down designs, mechanisms, and analysis tools. This presentation today is about techniques for managing and designing large assemblies. And the first thing I want to go through is the two different phases when we typically talk about large assemblies. So the first phase is what we call the top-down design area, which is how you create and develop a very large assembly or a very large product, how you establish outlines and interfaces, how do you distribute the work between different teams or different designers, and how you evolve the product that eventually becomes a large assembly. That area is what we typically call the advanced assembly extension that contains most of the capabilities under the top-down design. And then the other area is the large assembly management, when you already have a very large assembly in hand and you want to make changes to the design or to explore the design, to analyze it, or to develop new version of the product. This area is basically part of the foundation product, and all the capabilities are part of the base product and not necessarily require the advanced assembly extension. So I just wanted to clarify that point right away, because there is sometimes a confusion of what extension is required for what capabilities. So the advanced assembly extension usually talks about the top-down design, and large assembly capabilities are part of the basic Creo package. So let's first start off with the large assembly management. When we are talking about large assembly management, when you have a very large data set in hand and you want to access it or make any changes to the design, there are three main tools in PTC Creo that we offer today. And they address different types of capabilities and the different case scenarios. So the first case scenario is what we call the enterprise top-down design context. In that case, a user, for example, a CAD manager or a project integrator, can distribute different work contexts to different members in the team. You can do it directly from the PLM environment. It doesn't even necessarily have to go into PTC Creo just to create these contexts. He has a top-level integrated view from the PLM system of the entire structure of the assembly and also of the visualization of a very large assembly. He can distribute different areas to different designers to focus on. And it allows also to handle very massive structures without necessarily needing to loading them into the CAD environment. So that's the enterprise top-down design tool. Next is the user-driven subset. In that case, nobody prepares for the user that needs to make the design change upfront the context. The user can do it for himself while accessing Creo. He can do it on the fly, previewing the assembly and filtering down quickly the context of the assembly in the areas where he needs to perform his design task. And the last method is the dynamic context retrieval. In that case, we are using the lightweight graphics, and instead of defining upfront or on the fly what is the context or the areas that the user is interested to work on, the user simply loads a very quick representation, graphic representation of the assembly, and can on the fly load further details in the areas where he is interested to perform design changes. So let's go through each of these different tools. So the first tool is the Enterprise Design Context. In that tool, the user can access directly from HTML browser, either embedded browser or simple, any kind of internet browser you have. You don't necessarily have to do it from Creo. You can prepare it outside of Creo. It can be either the project integrator or the CAD manager himself. It can be also the designer himself to prepare the context for himself. So let's see how it works. First, I start having only the top level assembly in my workspace. I don't need to download anything else. I don't bring any dependent models, only the top level assembly into my workspace. So in that case, I have a truck. I downloaded only this top level object of the truck. Now I'm going into the information page and click New Design Context. I provide it a name, and this would be one work package, one context subset of the design. In that case, I'm going to focus on the rear axle of the truck. So now, still in my HTML browser, I get this very quick embedded visualization that uses Creo View embedded in the HTML browser, and I can start filtering my context. I'm focusing on this rear area here. I can see it both in the structure and in the graphics, and I define a proximity filter. Anything that is within 0.5 meters from this wheel will now be added into my context. Everything else will be filtered out. I can also further edit my spatial filters, add or remove stuff from this area, from this space that I'm filtering. I can also access the level of detail just like in a regular Simpreps in Creo, define graphics rep or master rep and so on, and further remove stuff from structure or from graphics. As soon as I'm happy with the context that I filtered for my design, I can save it. It's being saved as a file, and I can now open it directly in Creo. When I'm opening it in Creo, it automatically retrieves into session only the context that I filtered. So I have the top level truck. I defined this separate external simplified rep. This is called external simplified representation, this file. It points to the top level truck, and it contains only the areas of the truck that I filtered. So not the entire truck. The entire truck is not required to be loaded into session. The system loads only the components that I filtered down from this truck. Any change I'm making in this context will obviously be updated automatically in this top assembly, but I don't need to retrieve it. This is the power of using this external simplified rep. Now, if there are different designers, for example, one designer needs to perform certain design tasks on the rear axle, another designer needs to perform design tasks on the front engine, and so on, I can prepare different files, different external simplified reps that contains those different work packages for different designers. So they can work concurrently and retrieve to their sessions only the areas that they needed to perform their design tasks on. Another strong benefit of this external simplified reps is the capability to design, in addition to the context that you are filtering, you are capable to design additional stuff in the context of the ESR that are not included in the top assembly. For example, manufacturing gigs or add-on designs that should not go into the top assembly but should be designed around a certain subset of this top assembly. So for example, if you look at this motorcycle picture, if I need to design some assembling equipment or some manufacturing jigs, I can design them in the context of this external simplified rep without making any changes to the top model and without retrieving the entire top model for the design task. I only define the subset that is relevant. The subset that is relevant for this design. I filter out the components that are not required, and I can design new items that are not going to interfere with the top assembly. And again, one of the great benefits of preparing these external simplified reps is the performance that you get by doing it directly from the HTML browser, and you don't need to start from the CAD environment. It's especially powerful if you have very large data sets. Now let's go to the next tool. So the next tool is Open Subset. In this tool, nobody prepared upfront from Windchill the context that you need to work on. The user does it on the fly for himself. And this method doesn't require published Creo view thumbnails on the server. It works directly with the graphics information that comes from the Creo file. So let's see how it works. So here I'm clicking Open, and I have this button here. It's called Open Subset. Open Subset is basically defining a simplified representation on the fly. So I click here on the top assembly, and I get this very quick preview window in Creo that uses the native graphics, and I can filter pretty much the same way like I would do from Windchill. I simply box select on the graphics screen. I can filter by size, remove small components, for example. I can filter also by internal, external, and I specify these are the items that I want to retrieve. Everything else will not be retrieved. I can further tweak the context that I'm filtering. I can also tweak from the structure. When I'm ready with the context that I want to retrieve to session, I click OK. And at this point, Creo retrieves from the server all these items that I specified in the design context. Only these items are being retrieved into the memory. Everything else is not being retrieved. So in that case, I defined pretty much the same context, but instead of preparing it up front from Windchill environment, I did it on the fly in Creo. And the last one is the dynamic retrieval. So in this case, we are going to use the lightweight graphics. Lightweight graphics basically use the Creo view thumbnails and bring them into Creo Parametric in order to provide the user with very quick scenery of the assembly. It doesn't retrieve anything into memory until it's actually required to perform any modification. So let's see how it works. So here I'm going to open, and if you see I have under the Open dialog, I have this option that's called Open Lightweight Graphics. This option is available only if you have on the server or on disk available Creo view thumbnails, which are PVT files, OL files, and PVS files. These are the thumbnails that are used by Creo view, and with Lightweight Graphics, we'll make use of them also in Creo Parametric to provide very quick scenery. So if I click Open Lightweight Graphics, in a couple of seconds, it brings this entire top-level thumbnail. What you see right now on the screen is only the first level thumbnails of these sub-assemblies. So there is nothing currently in session except those very light viewables. This allows me basically to immediately start and filter out items that are not relevant for the design task. I can exclude the cabin, I can exclude other items, and I can also drill down and retrieve more detailed graphics in the areas where I'm interested to work on. So if you see in this thumbnail option, I have the options to expand thumbnails to next level, which will bring the next level in this sub-assembly, in this area. The next level detailed, the next sub-assembly is the more detailed Creo view thumbnails, or I can immediately drill down to all levels, which will go and bring part-level graphics for all the items only under this sub-assembly. So I don't need to bring into session the rest of the assemblies. I can bring only the items under this sub-assembly in this area. It also works with double-click. If I double-click, it behaves exactly like clicking this expand to next level. So when I'm expanding to next level, you'll see that it brings a little bit more detailed. If I'm going to expand to all levels, it will bring part-level graphics, which are similar to graphic representation. And again, it doesn't bring anything else to memory except for those thumbnails until you really need to perform any design task. So here I'm focusing on the wheel. I want to perform some design task in this wheel, so I drill down to all levels, and I'm hiding some, excluding some other items that are not relevant for the design work. So as you see, in this case, again, I dynamically prepared my context for the design without really defining it up front. I simply, on the fly, drilled down to the areas where I want to perform a design task. brought more level of details in the graphics only of the items that are of interest for my design task. Anything else I can either exclude or just keep it as a scenery in this coarse high-level graphics without needing to retrieve any further details of the graphics if I'm not going to work on this area. Now, how it works if I want to perform certain design tasks. So let's say I want to make some design change to change the position, for example, of this axle here. If I edit the definition of this part, you'll see that immediately the system changes on demand the wrap from lightweight graphics into geometry wrap on demand. On-demand mechanism makes the system intelligent enough to bring for me the minimum level of details that is required to perform a design task. In that case, since I'm changing only the position of this component, I only need the geometry wrap of this component, but also the system is intelligent enough to bring the geometry wrap of the parent of its component, because this part is positioned relatively to that part. So the system knows that it needs to bring the geometry level wrap of this component as well in order for me to perform this design operation. So the system is always intelligent enough to bring on demand for the user all the items that are required in the minimum level of details for the design operation. So it is always optimized for the minimum memory consumption, which means you always get the fastest performance and the minimum level of details in the graphics for the design task. If I would activate this part, for example, in order to make some geometry change, it would bring on demand the master representation if I wanted to edit some feature information, and so on. As soon as I'm done doing this design operation, the system will go back to the previous rep, and the on-demand mechanism will work only for the time where I need it to make a deeper level of details available. So let's talk a little bit about simplified representations. First of all, what are simplified representations? Why were they originally created? So the historic reason for why simplified representations were created is performance. There were typical different levels of simplified representations, from exclude, when you exclude an item it's not in memory completely, through graphic wrap, which typically brings about 30% of the model information into memory and makes only the graphics, part level graphics available with no geometry references. Then geometry level wrap, which is typically 70% and brings also geometry references like surfaces, items, and so on. And the full 100% master representations that brings into memory all the features and parameters level. This representation consumes the 100% of the components in session. So user always had the choice how much memory to consume depending on the design task. In Creo, we introduced the concept of lightweight graphics. Lightweight graphics doesn't bring into memory the real CAD models, but it uses the Creo view format. So Creo view consists of PVS, which contains the structure. It has PVT file for every sub-assembly, and it contains OL file for every part. That's the format that Creo view uses when you're opening the assemblies in Windchill or you're opening them in Creo view. We are making use of this information when we bring lightweight graphics. We first bring only top-level PVT files, and as the user drills down in the areas where he's interested in more details, we'll bring OL level information, which is more or less same like graphic ref. But since we never bring the entire information, only bring information in the areas where user is focusing on, typically the memory consumption would be much less than full graphic ref, because you would never need entire assembly in part level graphics. You typically need only some areas of the assembly in part level graphics, and the rest is either excluded or kept in this top-level PVT thumbnail. So other uses of Simpreps also, as I mentioned earlier, are the concurrent design context. Whether you use external simplified reps or open subsets, different users can access and filter different contexts of the designs that are relevant for their own design task. So they never need to load the entire assembly into session. They can work in their context that is relevant for their area, while the integrator can always get the top-level view and see how the assembly is changing and comes to life. And the other uses for simplified representations is part of combined states. Combined states also include other informations like styles, like wireframe, and other information like annotations and so on. These are used for viewing purposes or for drawings, or to simulate some manufacturing processes that are later documented in drawings and so on. So one of the questions that comes to mind is, what is the best way to get my design context up and running in PTC Creo? So one of the major factors that affect the capability to use either of those methods is what type of viewables, CreoView viewables, are available. If you don't use CreoView thumbnails on your PDM system, or you don't know if you use them or not, you can always use Open Subset. Open Subset uses the native graphics that are always saved when you're saving a Creo part. It's using the native graphic chapter from the Creo models. It doesn't depend on any pre-published CreoView thumbnails. If you want to use lighted graphics, you need to have the classic thumbnails available on the PDM system or on disk. These are the full PVS structure, the PVTs, and the OL files. These thumbnails are required for Creo to be able to load this very fast top-level scenery, as I showed you earlier. There are some customers in the market that are using what's called positioning assemblies. Positioning assemblies is a solution that was developed to support very, very massive structures that are practically impossible to publish with the CAD worker that is installed on Windchill. If the data structure is very massive, Creo sometimes cannot even load such a massive assembly. So instead of publishing full PVS and PVT files for the sub-assemblies, this method publishes only part-level OL files and skips all the PVTs by retrieving only part by part in their relative positioning space. That's why they are called positioning assemblies. And it results with a list of all the OL files in their coordinate system in space, and only first-level PVS files for every sub-assembly. It doesn't contain PVT files. For that reason, this recipe file doesn't support the lighted graphics. It only supports the Windchill design context, the enterprise design context, the first method that I showed you. So if you're using positioning assemblies, that's the fastest way you can quickly visualize and filter assembly. If you're using classic thumbnails, you can use either lightweight graphics or Windchill design context. And if you don't use thumbnails or don't know if you use thumbnails, Open Subset is always the fallback to quickly filter a context. There are other caveats that you need to be aware of for each and every method. So first of all is the accessibility. Design context is the only one that is accessible from browser, either from embedded browser in Creo or outside. The other two are available only inside the CAD application. The source, as I mentioned, the subset is the only one that uses the native graphics. The other two methods are using some form of pre-published CreoView thumbnails. That means in order to be able to use one of these two, you need to configure the Windchill CAD worker to publish those viewables for you. The Open Subset doesn't require publishing. lighted graphics and windshield design context. Lighted graphics is working only with the classic publishing recipe. Design context works both with the classic one or with the positioning assembly. As far as speed, all of them are relatively fast, much faster than retrieving the entire assembly in Creo or even in graphic web. The fastest one is lighted graphics. The open subset is also very fast, but it's the least. It's not the fastest one of these three. But it's still much faster. And again, if you don't have any other option, this would be your fastest way to go instead of opening full graphic web. In terms of graphics fidelity, lighted graphics before you drill down, it has a very low fidelity, coarse, top-level thumbnails. Only when you start drilling down, it brings more information into the graphics area, in the areas where you are focused on. The other two are using part-level graphics. That's why the graphics fidelity is higher. So if this is something that's important to you, while you're defining your working context, either one of these two would be suitable. As for structure availability, all of them have exposure of structure information. One caveat for open subset is if you start expanding the nodes in open subset, it's not working just with the graphics. While you're expanding the nodes, since we do not rely on the TBS structure from Creo view, Creo must retrieve the subassembly objects into your workspace in order to resolve the next level underneath them. So expanding subassemblies nodes will retrieve these nodes into session. Typically, it's very small file because it's just the subassemblies. It doesn't contain part levels, but it will have more items in your workspace when you try to access the structure. As for filtering, there are different types of filters available for every method. So the open subset has the filtering by size, by internal, external, by box selections, or explicitly in structure. Lighted graphics basically allows you to filter directly in the Creo graphics, either explicitly on the structure or by 3D box select. And the windshield design context has a little bit different filters. It has spatial filters, proximity filters, explicitly in structure, by name, or by dependencies and other PDM attributes. Okay, so this was the phase of large assembly management. Now let's go back a little bit in the phases of a typical design project and look in the first phase. How do you start a very large design project? How do you establish those outlines of a system? How do you communicate them to different users in the system? How do they collaborate and evolve the design? And how do you execute late changes in a design? So this talks about the top-down design. So what is top-down design? First of all, the basics. Top-down design typically starts with either conceptual design that is done many times in 2D, sometimes preliminary structure, and then we reach the 3D skeletons. Skeletons are used to capture the design intent of the entire systems and the typical common interfaces between the systems that you are going to design. From skeleton, then you go on and publish the design intent through data Shrinkwrap features down to the components that are needed to be designed around those different curves, different surfaces, different interfaces. And then when you start and adding more details to the design, you can start and manage their interdependencies by defining certain reference control restrictions, and I'll elaborate a little bit later. And eventually, as soon as the system starts taking shape, you populate the assembly. This is an iterative process where you add more details to the components. You sometimes edit the skeleton, add more details to the skeleton. The system evolves and eventually takes life around the skeleton outlines that you defined originally. So what is skeleton? skeleton is a central object that allows the user to capture the entire design intent of the entire system. Typically, it consists of only abstract system outlines. It looks like a cloud of different entities that are only relevant for 2 or more components. It has common outlines and associative references that are going to be used by multiple components further down when you are going to design around them. And it allows to distribute to different designers those different areas, different design spaces where they are going to design around. So how the data flows from a skeleton down to features and components. From the abstract skeletons, we are publishing the information through data sharing features. Every component in the design will get the data sharing feature that contains the outlines from the skeletons that are relevant for this part. And then in this part, the user can design around those outlines and add more detailed design geometry. The real strength is when working with multiple designers. So if I am the integrator that is designing this motorcycle, for example, or this bike, I can define those outlines very, very quickly and establish those common outlines, those common geometries to the different people in the team. Each one of them can get the relevant information that is relevant for his design task. This user needs to design the fork, that user needs to design the rear suspension, the other user needs to design this gas tank. All these users can get this information populated to their area and can design around the area that they are responsible to, and they can do it concurrently. They don't rely on each other and they don't wait for each other to complete their design because they already get the relevant outlines populated from the skeleton. So this integrator can see all the details comes to life around the skeleton that is defined up front, while those are being done concurrently instead of one waiting for the other to complete his work. That's one of the major strengths of working in a top-down design method. Now the real strength comes when you start making iterations to the design. Since everything is captured in this single object that contains the entire design intent, I can easily change the design very quickly without doing multiple subsequent changes to the components that are already designed. So let's say I want to change these dimensions in the skeleton. I can do it quickly once in the skeleton and regenerate the entire system, and everything will update to the new dimensions because every design here is basically associated with the outlines that came from the skeleton. And that's why top-down design allows you to very easily and very quickly not just design concurrently a large assembly, but also populate very large design changes very quickly. What are data sharing features? So we talked about how we communicate information from skeletons to models. Also, data sharing features can communicate information from a model to another model. A data sharing feature is basically an associative copy of certain parametric content from one model to another. It allows you to reuse and to manipulate designs of multiple objects by single parent. So they can either be used from skeletons to submodels or from one model to another. It doesn't matter, it's user's choice how to do it. Typically, the best practice would be to do it from skeleton to models. However, in many real-life design cases, you would skip overloading the skeleton. You will share directly from part to part without doing it purely top-down. So what kind of data sharing features do we have? The first one, the most common one, is copy geometry. Copy geometry is copying surfaces, datums, and curves from one model to another. It also works with published geometry. Published geometry is a feature that can be defined in a skeleton level, and when you're populating a copy geometry into the target skeleton, instead of selecting individual surfaces, you can select a published geometry feature from the skeleton. So you select only one one intent object instead of selecting directly the references. Another data sharing feature is merge. Merge allows you to basically add or remove full solid geometries from one part, either as add geometry or as a cutout, as remove. And the most advanced data sharing feature is inheritance. Inheritance allows you to take a complete design intent from one object to another and also apply variations on the copied content. For example, I can copy this set of orange features into that model, and they can also apply certain variations, for example, on the diameter or on the length. And like merge, it can be copied either as remove material or as add material. We can apply variations on any parametric characteristics of this design, and we can also maintain associativity to the original design. So if I didn't apply any variation to this length, when this length changes in the original part, it will also change in the target part. Now this is the coolest thing that brings everything together, from top-down designs with data sharing features and populating the design. Motion skeletons is all the package in a very nicely automated fashion. How it works. Users can define an assembly of skeletons, if you will. By starting with defining those outlines, you can then start and defining different skeleton bodies in this skeleton assembly. Creo can automatically detect by certain logic these contacts between the curves and suggest the user automatically with different kinematic constraints between the different skeleton bodies it is defining. Usually when two curves have a mutual corner, Creo would suggest to identify this corner as axis or as ball joint and so on. User can of course change this definition if the automatically detected one is not suited. In most cases it would be more or less like sketching on a napkin. Creo would typically suggest exactly the type of connection that the user meant to have. And then when those skeleton bodies are defined, user can add parts and attach them to the skeleton body. When user attaches the part to the skeleton body, the part moves with the skeleton body that already has its kinematic connections. But in addition to that, Creo also automatically creates the data sharing feature in the target part. So all these outlines that are defined in the motion skeleton will automatically be shared to the target part that is attached to a skeleton body. So this entire design process, from a quick and abstract outline of the system, through defining high-level mechanism, through defining the full detailed geometry, it all happens very automatically and very cleanly from top to bottom. Another advantage of this using motion skeletons is that it allows you first to analyze on very high, on very low details and very early stage in the process. You can make dynamic analysis, motion analysis of the system and optimize it even before we have a complete detailed design. Another advantage is that if all the kinematic connections are defined in the motion skeleton level, you can basically exclude easily every part in every real detailed part and still maintain the motions without needing to have all the real geometries in session. So it also helps to get the maximized performance if your assembly is built around motion skeleton. Another very strong capability around the same area of advanced assembly is the interchange groups. Interchange groups allows you to make modular designs. What do I mean by modular designs? It means that every part that is intended to be a model that can have more than one optional design can take place in exchange for the part that is currently in the assembly. For example, let's say I have this bike. This bike has a certain design intent. It has a frame and two wheels, and each of these wheels has its own axis where it's connected to. So it doesn't really matter if I have this frame or that frame. They will connect to those wheels by exact same interfaces. And same goes for the wheels. Let's say I have more than one wheel option that I would like to use. Each of these wheels will connect exactly the same way to the frame. It has this axis and the central plane. So I don't need to define over and over the same design intent if I already have a design intent of a bike ready for me. All I want to do is to be able to quickly switch from one option to another. So how does it work? First of all, you define what are your models that are going to be available for this design. In this case, I have two models. I have the frames and I have the wheels. Next is defining those common interfaces. We call them tags. Tags specify what is the equivalent interface in the other models, so in the other options for these models. So in this model, this is my fork axis, which is the same axis in this frame. And if there are other frames, the same tag would be used to specify which is the front axis for the fork in this frame and that frame and all other frames. Same goes for the wheels. It has two tags because it has two interfaces. The interfaces are its front axis and its center plane. Same tag goes for all same interfaces across the different options for the same models. Once a tag defined, this is your interface to the outside world. All the ingoing and outgoing references will look for this tag in this design. Next is defining the structure. So that's design intent. If each one of those components is positioned to the assembly, interfacing to the assembly with the references that are being tagged here. And then I can easily change my design. So if I want to change from one frame to another, as soon as I'm changing, the wheels will automatically adjust to the new geometry of this frame because they know they need to look for this interface to connect. So this is the very basics of a modular design. This is a design that has few options, not many options, and user would like to manually switch and change the different options that he's using in his design. If you have highly configurable products, you should learn more about Options Modeler. I'm not going to talk about Options Modeler in this presentation, but if your product is highly configurable and you have very frequent changes of this sort, I would recommend to get more information on Options Modeler, which is an application that is dedicated specifically for this type of product that have massive models and a lot of options that can be applied for configurable products. And it works also with the PLM environment and can bring the specifications for configurations directly from Windchill and interact with Windchill options variant capabilities. So this is just the basics. Options Modeler technology is using this technology in a much more advanced form. A few more capabilities of the advanced assembly is the Shrinkwrap feature. Shrinkwrap feature, very much like the other data sharing features, is both a simplification method, but also a form of data sharing feature because it allows to maintain associativity. It's basically used for simplifying very large assembly into a single object that contains some or all surfaces or geometries from the original assembly. It can be used either simply for simplification. If you don't want to load the entire subassembly into memory every time you work with this assembly, you can prepare a shrink-wrap and next time load only that shrink-wrap instead of this subassembly. It can also help for IP protection if you want to share certain assembly to a partner or to a vendor and you don't want to expose certain details, you can provide a shrink-wrap that contains only the relevant information without exposing anything inside. So let's see how it would work in this type of case. So let's say I have two different designers. One of them is responsible for this chassis. The other one is responsible for this exhaust system. The user that needs to design the exhaust system doesn't have permission or doesn't have a need to see all the internal details of this engine. So this user can prepare a shrink-wrap of this motor and send it along with this chassis to the other user. While this user starts designing the exhaust system, the other user can still further evolve and iterate the design of the chassis and the motor and so on. Now remember that this user now is working with a shrink-wrap that may not be updated anymore. And Creo is intelligent enough to forward references if anything has changed. So as soon as this design is done, the exhaust system is done, and checked in windshield, for example, this user can take the design that was referencing the shrink-wrap and replace it with the original engine. When he's doing this, if, for example, this surface that the exhaust system was referencing now is moved in the real part further down, the system will update both designs because it will forward the references. It knows, it keeps information of the associative references that were used for the outside surfaces of the shrink-wrap, and it knows to update them once you replace the shrink-wrap with the original part. So Creo tracks each and every surface ID, and it knows exactly where it came from. So when you replace this shrink-wrap with the original part, the system will automatically forward the reference to the real part. And as I said, it's also very useful for IP protection, not just for performance reasons, but also for IP protection reasons if you don't want or cannot share certain details of your design. One note here, this is only working, the forward referencing is only working with Shrinkwrap feature, not save as Shrinkwrap. This is one limitation for save as Shrinkwrap. Save as Shrinkwrap is just publishing a simplified form, but it wouldn't support the associativity. So for having the full associativity, you need to use the Shrinkwrap feature. Okay, so we are close to the end. So last few capabilities around large assembly techniques. So first one is structure handling. Those of you that remember before Creo 2, or those of you that are not yet on Creo, this drag and drop capability was introduced in Creo. Instead of working through dialogues of restructure or reorder, this is single point of access capability. You simply drag and drop in structure. When you hover over a subassembly, if you wait a couple of seconds, it will expand the subassembly. If you just try to drop the dragged component between nodes in structure, it will just reorder them. If you want to restructure, you need to hover over the subassembly, and it will simply expand it and let you also restructure the component. This is something that was introduced in Creo. So those of you that are not yet on Creo, this capability is part of Creo, the drag and drop. Another very, very cool feature in Creo is the simple search, also something that wasn't available in earlier versions. It allows you to quickly search in the model tree and also get this color coding in the graphics and in the model tree. You can also filter the model tree, add items to selection, and you can also have a history of the searches. In this drop-down, you will see the history of the items that you have looked earlier. You can also find by different states, for example, not just name, but also frozen items, packaged items, failed items, and so on. So this is a very powerful capability to either find items of interest by name or quickly locate issues in the assembly like packaged items or frozen and failed and so on. And the last slide here is about track changes. If you are working a lot of time in your session and you want to review what you have done through the session, you can always right mouse button on any sub-assembly or top assembly or any part in the design and invoke the track changes dialog. Track changes dialog color codes on the left of the model tree the different types of changes that you did. You have this nice legend. You can track different changes to a design, renamed, modified, replaced, and so on. Very easy to locate all the changes that you did through your session and also to review them in the graphics. Everything is color-coded. More importantly, this dialog pops when you work with Creo Direct. If something was changed in Creo Direct, typically Creo Direct users may not be aware of the parametric consequences of their changes. So the next time a modified model, a model that was modified in Creo Direct is saved and later opened in Creo Parametric, this dialog will automatically pop up, list all the changes that were done in the Creo Direct environment, and also allow user to accept or reject each of those changes. So Creo still keeps those changes very safe and allows the parametric user that can analyze those different impacts of the direct changes and either accept or reject those different changes to the design by investigating them in this dialog. And I think that's pretty much it. I'm now open for questions.
Thank you, Moshe. Looks like we don't have any questions currently. So if you all do think of any questions down the line on this subject or others, you can feel free to reach out to your TriStar representatives. As I mentioned before, the presentation was recorded and will be posted in our Resource Center. You can find this by going to tristar.com and clicking the Resource Center link at the top of the page. You can also check out upcoming events by visiting tristar.com/events. Thank you all for attending again. And once again, Moshe, thank you for your presentation. We really appreciate it. Have a great week, everyone, and we'll see you next time.
Thank you, everyone.